Hi, my name is Timothy Murray. I am a current senior at Cornell University studying mathematics with a minor in computer science. I'm applying to the Mathematics PhD program at the Courant Institute at NYU. My area of interest is optimization methods, specifically in numerical analysis, financial, and discrete mathematics. Because my area of interest spans several fields within mathematics, as well as my background in computer science, I believe I am best suited to study applied mathematics with an emphasis in optimization. The problems that particularly interest me are in scheduling optimization. However, longer term, I would be happy to work in any field that offers a significant number of optimization problems. Optimization particularly interests me because many of the problems which involve it are either NP-hard or NP-complete, meaning that if the problem is large enough, there is often no practical way to determine if your answer is the best, only if it is the best to date. Now, for one-dimensional cases, this is often not a problem. For instance, if we're trying to maximize the function f of x, as seen here in this graph, we can simply look at the graph, determine that f of x is maximal at f of x1, right here at this point, and that there are three other local maxima, but they are not quite as large. Now, if we go up even one more dimension to f of x comma y, as shown in this surface here, we can see that the problem just got a lot harder. Now, oftentimes these surfaces are much less nice than this. We have more than 4 local maxima. We could have hundreds or thousands. And there also comes the problem, what if we can't actually visualize this surface to check each of these local maxima? Well, what do we do then? This is often the case for problems that are beyond 2 dimensions. 3 or 4, it becomes virtually impossible to visualize these sorts of things. So we have to come up with a better method. I would like to come to NYU in order to be one of those people developing the better, more clever methods for optimization. I believe I would be an excellent candidate for the Mathematics PhD program at the Courant Institute because I have a great deal of experience both in my own field of optimization as well in a more pure mathematical field, specifically analysis. I recently completed a 2-month term project for the course CS 5724 at Cornell, which focuses on evolutionary computation. My project used genetic algorithms in order to solve the multiple traveling salesman problem, which is a specific case of the vehicle routing problem. I addressed several specific instances where they also have no common supply depot, meaning that no 2 routes share any common cities between them. A link to my report for this project is available here on the bottom of the screen, as well as in my application. Now, since June 2014, I've been working with Professor Bob Strichertz at Cornell to examine the average error of Weil's asymptotic law, which predicts the number of eigenvalues of the Laplacian on a given region R in a space of constant curvature that are less than a given value t. Specifically, we've been addressing the rate at which this average error goes to 0, with our prediction being that it decays at a rate of approximately t to the -1/4. Our results seem to corroborate this assumption, and we've completed most of our test cases. We are currently working on a paper, 5 pages are complete, and a link to the results that we've obtained so far can be found here at the bottom of the screen, as well as in my application. It is for these reasons, my experience both in and out of my chosen field of optimization, that I believe I would be an excellent candidate for the Mathematics PhD program at Courant.